For me, it's a pleasure to present today Dr. Thomas Schmid. Thomas Schmid is a physical geographer from the University of Zurich in Switzerland and is doctor in chemistry from the Autonomous University of Madrid, Spain. Thomas works as senior researcher at the CIEMAT in Madrid, and he has a strong background in soil science, geomorphology, and remote sensing. And his research is centered on characterizing and monitoring soil processes and land cover changes. Thomas is involved in Antarctic research since 2005, this is almost 20 years, and participated in SCAR groups, such as the Permafrost and Soil SCAR group. Now, he is co-principal investigator of an Antarctic project that is preparing the next expedition in January 2025. Let's give a warm welcome to Thomas.
Well, thank you very much for the introduction. I would like to give my thanks to Asunción and Mireia for the organization, for inviting me to this event. It's a real pleasure to be here in such an amazing place as the CSIC, the museum. It's a real honor to be able to present my humble work, which I carry out in Antarctica. To be honest with you, it's fantastic to be able to work there. So being able to go on expeditions and carry out your work in such a place is really amazing. So today, I want to talk about different techniques in remote sensing to be able to determine work we carried out, which I'm going to explain now in some detail, and to be able to characterize this. So my contents will be a short introduction with objectives, the study areas we've been in Antarctica, geoindicators as an approach to landscape monitoring, and the application of reflectance spectroscopy and spectral libraries, and how we apply these remote sensing techniques. We work in ice-free areas. So what are the ice-free areas? Antarctica, as we know, is mainly covered with ice and is under an ice sheet with several hundreds kilometers of ice. But when it comes to the coastal area, these ice sheets start to give way to areas which we call the ice-free areas. The ice-free areas are nowadays exposed land surfaces, and they're there, especially we always go there during the austral summer, but during the winter, of course, snow and ice does cover them, but during the summer, it melts. So we have access to these areas. So these ice-free areas are really small extensions, mainly along the coastlines of Antarctica and the islands where we normally go to, the South Shetland Islands. And it's about 1% of the total area of Antarctica, so a very small area. The ecosystems under these areas are really under harsh conditions, meteorological conditions. So any types of life which can occur there have to survive the harsh winters, and therefore reducing any biological, chemical activities and processes. They're also hotspots of biodiversity. These small areas, especially in the summertime, is where all the fauna, the flora gathers. Also us as humans. We come to the bases and we carry out our activities there. They are known to be sensitive to climate change. And in the northern Antarctic Peninsula region, it's an area which is especially known for the greatest warming within the southern hemisphere over the past 60, 70 years. So we have to take into account the natural changes that can occur, but also the anthropogenic activities, especially around the bases. And in this case, we can use remote sensing techniques where access is limited and where small ice-free areas are really dispersed along the coast. So it's an ideal way to map and monitor land surfaces. So the objectives we've been pursuing, it's not just me working in this, it's a whole team working. So the objective is to determine the distribution of different terrestrial land surface covers of these ice-free areas in Antarctica using the different remote sensing techniques. I listed a few of the most common specific objects we carry out because we want to monitor these highly dynamic and complex landscapes. We compile spectral libraries for the areas we study. We use reflectance spectroscopy to extract information. So we have different types of sensors, which are in satellites, which obtain this information. We have to pre-process, and then we have to process this information. But this is the information we want to look at. We want to map key soil properties, which are indicators of the flora, fauna, using imaging spectroscopy. And in the end, what we obtain is a spatial distribution of these different landforms, which can be periglacial, glacial, paraglacial, using these different types of sensors. If we have a quick look at this less than 1% of the area which these ice-free areas cover, we can see they're especially along the coastline of Antarctica, and they're normally also mountain ranges which stick out of the ice in areas where the ice has receded, especially in the northern Antarctic region. And so the circles which I've drawn here on this map, these are the areas where we've been working in. When I talk about geoindicators, it's really an approach which has been developed by the International Union of Geological Sciences to be able to do landscape monitoring. The idea is to be able to treat all types of landscape, but I'm going to concentrate on the ones we can find, especially in the ice-free areas. We talk about the hydrogeology, where we study lake levels. The changes can be drawn by stream flow, groundwater flow, or the groundwater chemistry is very important in the unsaturated zone. The groundwater level, abstraction and recharge are some of the changes which can occur. And the groundwater quality, the normal rock and soil weathering, but also pollution can come into it. It can be natural or it can be anthropogenic. When we talk about glaciers, we look at the glacier fluctuations. The ice-free areas are exactly the border between where glaciers used to be, they're receding, and they're opening up a new area. This new area is particularly interesting. These are areas where there's a really dynamic system which is active. And that means that any changes with these fluctuations will have quite big consequences. So it's interesting to be able to limit the extent of the glaciers. We talk about soil and sediment erosion. Here we're in an area we can see just a small stream. But in some times during the year, there must be a lot of water running through these areas to be able to create these gullies. We're looking at here at gullies, which probably the water flow is just 3 or 4 months a year, but during that time, the erosion is extremely high. But you can also see on the higher surfaces, we have erosion through wind, through water, and then the gully formation, and all the sediments which are carried out towards the sea. What does that mean? Especially when there are changes, like we're experiencing now with climate change. That means there's a lot of minerals being liberated, especially iron, phosphorus, and this is all goes to the sea, can change the whole ecosystem of the marine area. So it's really important to be able to study this. When we look at the areas at the headwaters of these canals, then many times what happens is the accumulation of snow forms into ice and it blocks all this water to the point when there's so much pressure that all the water just runs out, maybe in a very short time. In a few hours, all the water is in the coast, but it takes with it all the sediments. And this is at when it comes out to the coast, these channels form the deposits of the sediments, and they can form catastrophic events. And these events are interesting to be able to study. So here we have an example of what happens in a really dynamic area of the ice-free areas. Now this, I'm going to take as an example of soil quality. Of course, we're looking at an amazing mountain range. This is Victoria Land. The New Zealand group works here. I can see people in the audience know this area. But what I want to point out is this small plot of land, which is called CB Hook Cape Hallett. It's an area where about 47,000 penguins rest. They come here to breed. And of course, they deposit their guano, and this is really interesting for soil development. So here we can actually see how the land is used, the chemical, biological, and physical soil processes, because there's an input of carbon, an input of nutrients, which help the microorganisms form the soil, which there, again, carry out all the processes, the edaphological, pedological processes, which occur in this area. So our areas of interest, as I mentioned, are the northern Antarctic Peninsula area on the left-hand side, and areas which I haven't visited, but people in our project have, and they go there occasionally to carry out their research. But the good thing is they bring back soil samples for us so we can analyze them and we can carry out all the studies of those areas. Over the years, we've developed a method which is quite simple. It's integrating all our data into a common database where we, in the end, are able to have a distribution of sand surface land covers and our geoindicators, which we're studying. We have one part, which is probably one of the most important, are the field sites, because we have to validate all our data. We have to calibrate our data. So this is a really important part when we go out to the field. We obtain our field samples, we study abiotic, biotic parameters, then we're able to study the soil samples, carry out our reflectance spectroradiometry, create spectral libraries, All these terms I'm going to explain now, but it's just to give an oversight also of all the optical, the radar, aerial photography we can use to carry out our analysis and then have supervised classifiers, create models to obtain our final result. Of course, there are many studies which have already been carried out. And we try to incorporate this also into the database because it's really valuable. With remote sensing, we have the remarkable advantage of going back in time because we can go back into the 80s. So we have a whole group of people which study different elements in the ice-free areas. I just want to quickly talk about the remote sensing we carried out. Just for those which are not familiar, when we talk about remote sensing, reflectance spectroscopy, we're talking about electromagnetic radiation which arrives at the surface, our surface which we're studying, and this reflected energy is then detected with a system. Our eyes actually are remote sensors because we don't actually go and touch what we see in the distance. So this detection system obtains the information and we have to process that. Different materials can absorb light differently. We know a black surface will absorb more energy than a white surface which reflects it. Also depends in what part of the electromagnetic spectrum we're talking about. So here, just to remind ourselves, the different parts of the electromagnetic radiation. We have a visible part, we have the infrared, thermal infrared for optical sensors. We have the microwave radiometers, the radar with its different bands. These are the sensors we normally use. And here we can also differentiate between passive systems which depend on the reflected light or the reflected energy which a sensor receives. But we also have active systems, namely the radar systems. They emit a pulse. And this pulse is then received again by the sensor. And that's the information which is reflected also from the surface. And all that with the satellites, which have the advantage that there's a revisit time. So they can repeat this. And having a repeated information allows us to carry out the monitoring and also detect the changes. These are orbits normally for Antarctica, which are the polar orbits. So the sensors maybe have a revisit time, depending on the height, 600, 700 kilometers above the Earth's surface, that they revisit every 12, 14 days. But that's very good for us, and we can actually obtain the information we're looking for. There's also a difference between image characteristics. When we're looking at optical sensors, we differentiate between what we call multispectral sensors and hyperspectral sensors. Talking about radar, we also have radar in different bands. These bands are delimited by the actual wavelength which the sensor works at. We talk about C-band, which is within the centimeter range, the L-band, which is tens of centimeters, meter range. So we have differences, but one of the big advantages of radar in comparison to the optical sensors is that the radar functions in all weather conditions. It penetrates the clouds. It's able to obtain a signal from the surface. We have to be careful, though. Depending on how the surface is or the weather conditions, the signal does change. So we have to know if it's been raining, it hasn't been raining, it's a dry system, etc. But the advantage is we're able to obtain a signal even if it's cloudy, whereas an optical sensor is not able to do that. With the optical sensor, it doesn't work. If there are clouds, we don't obtain information. And in Antarctica, especially in the northern Antarctic Peninsula region, we'll often have clouds. So our data acquisition, when we're out in the field, we have what we call a spectroradiometer. This spectroradiometer is portable. We have it on our back. We calibrate with what we call a white reference. We obtain different surface covers. This is exceptional. Afterwards, I'll go into this, to be able to do it with sunlight in that area. We normally have to use artificial energy, light, which illuminates an area underneath this apparatus to be able to obtain our spectral curve. Or we have a contact probe, which we're actually touching the surface with a bare optical fiber to obtain a signal. We can also carry this out in the lab, of course, and we often do that. All our samples we obtain from Antarctica, they're so precious, we go back to the lab and we measure it in the lab. In the optical range, we use the multispectral sensors like Landsat 8, Sentinel-2, their whole generation of Landsat. They go back to the 70s. And now there's Landsat 9. Sentinel is a new generation of ESA satellites, which are also developing new sensors. I'll come back to that. Then we have the hyperspectral optical sensors like Prisma, like ENMAP. These are the new generation experimental satellites. But now they're going to make more useful hyperspectral sensors which will be able to be used the whole time. Then we have our radar sensors, Sentinel-1, RadarSat-2, their whole generation. They've been very active, especially in the polar regions, or also in regions where there's a lot of cloud cover, like the Amazon basin, the tropical areas. So radar is a very common type of sensor to use in those conditions. Our field acquisition data, when we're trying to relate our field data with the satellite data or a sensor which is over the surface, we have to think of how do we carry out the spatial distribution. We've come up with a technique where we sample over a larger area. That's to be able to identify well in our satellite images the actual area of interest, because we always have some error with the GPS. Doesn't matter how good your GPS is, there'll be an error. And also with the representativity of the actual area. The surface area can change a lot in very short time. So the idea is to be able to have an area well determined where we can take our field spectra, we can take our surface samples, we can do all kinds of measurements, all within what we call a test plot. And these sub-test plots, at each sub-test plot, we carry out measurements. So in the end, we have statistically a very representative data which we can afterwards use as reference. So this is where we come to our spectral libraries. Our spectral libraries are field data and laboratory data, which we bring together. And we have well georeferenced all these points. And we use these to calibrate and validate our data. So we can have bare soil surfaces, we can have vegetation surfaces, we can also have surfaces which are occupied by penguins with the guano to be able to identify them from space. There's work which has been carried out, especially by the British Antarctic Survey, that people have been able to determine the penguins on the ice sheets, the penguin rookeries on the ice sheets, and see how big their populations are to give an estimation. Because many of these rookeries are inaccessible, and no one really knew how many penguins, emperor penguins, or whatever type of penguins are, existed. So this is one way of being able to spectrally determine the guano, and then through the satellite we can determine how is the distribution of patches of guano, which can be huge penguin rookeries containing 50,000, 100,000, 150,000 penguins, and of course the area is huge which they cover. And also our laboratory spectra is very useful because we can create models that permit us to determine different soil properties, for example. So the spectra of different surface covers are interesting, and often where I especially work in the area of soil, I'm looking for soil, but it's covered with vegetation. But that's a good indicator. But what we do is we obtain the spectra of both the surface, which can be covered with lichens, mosses, and of the soil underneath this vegetation cover. And this then allows us to relate this with soil analysis from the lab, and we can see how this vegetation on what kind of soil is really occupying. So we can have a good idea through the vegetation what kind of soil formation we're obtaining. Now I put the title of this picture consciously at the bottom because we're looking at an ice-free area, Cierva Point, which is now on the coast of the northern peninsula, Antarctic Peninsula area. But what I want to show is this sky. This is just marvelous for someone who's working with remote sensing and has to go out to the field, because probably 90% of our time is with cloud cover. It's a real, not going to say the word, but it's molests. So to have this kind of sky is incredible. And that's where we carried out our work. We were able to obtain perfect field spectra for one day in an area with no cloud cover. And the most amazing thing, and I don't know how it happened now still, is that when I came back from the expedition, I was looking up, well, I'll go and see what image, multispectral image, is available. On the same day as we were taking our measurements, we had an image. Now you can't do better than that. Even with all the organization you carry out, you won't get that. That was real chance. But we were able to obtain a cloud-free image. It's a multispectral image. But we could carry out a very good classification. And of course, we can validate it. And in the end, we get an accuracy for different covers, which go up to 80%. Here I put 100% with wet snow, but that's obvious because the spectral curve for wet snow is so dominant, so it's no problem. But other surface covers, moraine deposits, clasts, penguin rookeries, we could even determine not so well, because we have to think that we have a 30 by 30 meter pixel. And these penguin rookeries in this area are very patchy, they're very spread. But anyhow, we could determine a very good land surface cover with an image, but this is exceptional. I haven't been able to repeat this in Antarctica with the expeditions I've been on. This is what normally happens. We have cloud cover. Cloud cover will affect the image, but we can mask it out, and we can still take profit of the areas which are not covered with clouds. Here, we're using a hyperspectral image. Of course, that's a huge advantage. And we have a much better signal, which we can afterwards interpret and be able to go to our spectral library and compare and be able to give it a label. And here again, of the areas which are visible to the sensor, we can obtain pretty good classification. The classification is even higher than before because now we're using a hyperspectral sensor. So having this information with many bands improves it a lot. Now I'm coming to an area which is called CV Hook, Cape Hallett. Before we saw that incredible image with the nice mountain range. Going in more detail, this is the area where all the penguins are. 47,000 pairs breed on here. It's an Adelaide penguin colony, and we used it as a purpose to map key soil properties that are indicators of the flora and fauna which are present there. So soil samples were collected at different sites. They can be penguin mounds, they can be in between penguin mounds, they can be areas more vegetated, etc. We did laboratory analysis, organic carbon, total nitrogen, phosphorus, and then we acquired a hyperspectral image on this date, and we processed this image using machine learning and regression techniques. These are the typical curves we obtained from the sensor. And these are the type of analysis, the values we obtained for the different soil samples. I did an average of the soil samples in the active mound, in the abandoned mound, etc. Because penguin colonies are very complex. I'm sure some of you here work with them, and they're complex areas. So we got average values, and we could determine how the different nutrient content is, etc. And what we did is obtain a quantitative value of total organic carbon, total nitrogen, phosphorus content. And this is something we have to think. We're using a satellite image to obtain this quantitative data. It's very valuable because like this, we can actually, if we have a good model, a good area test site, we can extrapolate this and see how other areas are with the quantities of nutrients here we can see. So this is a very good example. Of course, it's quite a lot of work behind it with processing the data and using the different algorithms and getting the best data. But we've been able to obtain a very good measurement here. Now I want to show you also predicting soil properties using reflectance spectroscopy. We're going to the lab. We're using our soil samples. Now these soil samples, of course, are measured under controlled conditions. But so are our analysis in the soil, in the lab. When we analyze soils, we also measure or analyze the soils at less than 2 millimeters, etc. We're also conditioning the soil. But it's a way to be able to relate what we obtain in the lab with what we obtain with the spectra. Now, the interesting thing is we carry out a simple regression analysis, partial least square regression analysis. And for iron oxides, organic matter, clay, sand, we can obtain values of up to 88%, which agrees with our lab analysis. So we can obtain very good models to afterwards predict soil properties. So we can go to any soil sample, we can put it in our model, and we can predict. We did an observed analysis in the lab, and then what we predicted with our model. So we can get pretty close, at least to give us an idea in what range we're in. And this has the advantage, of course, we can analyze many more samples. We don't have to use chemical analysis. It's just preparing a sample, drying it, sieving it, and then we can measure these spectra. And like this, we can obtain groups of soils and decide if we want to have a more accurate measurement. This isn't 100% accurate like if we carry out a lab analysis with a specific instrument, but we can obtain a very close value. And that's very useful in a very short time. So this is another way or another option we've been exploring, because we bring back hundreds of soil samples, and these have to be analyzed, and it's time consuming. So if we can go through this way, we can actually group and see what's of interest, how we're going to, or where we're going to focus, etc. Now I'm going to give you more of some example when we're looking or treating not just with optical sensors, but also with radar sensors. As I said, radar sensors have the advantage that data can always be obtained, night and day, in any meteorological condition. So here we're in King George Island. We're looking at, excuse me, we're looking at Fielders, We're looking at Fielders Peninsula. It's an area which is very active with human activities, lots of bases, an airport, a very interesting place. It also has natural areas, of course. And we've been studying it as a reference test site. We have different surface covers, of course, even glaciers. But here's an idea of the bases, accumulation of bases we have. So we have geomorphological maps available, which have also been taken partly by our team and created. We have a supervised classification using radar data. And once we have this from a test site, we can start to extrapolate this over a wider area. As I said, a lot of these ice-free areas are quite small. Here in Fielders Peninsula, we're talking of an ice-free area about 28 kilometers squared, 30 kilometers squared. But they can be much smaller. They can be 1 kilometer squared. So these are not really accessible areas, but we can use our model to be able to go to a wider area. We can cover the whole of King George Island with two, here in this case, radar sat images. We're using fully polarimetric data. And this has been processed so we can cover the whole island. And these are interesting results, because in the end, what we obtain is the surface cover, the percentage of area which is covered by the different land surface covers. So like this, we can obtain an idea of how these areas are. If we obtain an image in the future, then we can compare and see if these areas are growing or becoming more bigger because of the receding glacier, etc. We can also use radar, which is really good for delineating glaciers. Here we're on Elephant Island. This is the so-called Endurance Glacier. Maybe it reminds you of Shackleton and his voyage. But what we've seen is that from original glacier extent in the 50s to nowadays, it's been receding. It's a glacier which went into the sea, and nowadays it's on land. What we did is estimate how much this glacier has receded. We're talking of a time period, of over 50 years. We've estimated the volume over this time period by using the information we had from the 50s and from actual information nowadays. And we estimated that it's 1.795 cubic kilometers that it's receded. It's a lot. And that was between 1957 and 2009. So 52 years. We can now get another image and do the same exercise. Then we will probably have the ice front even further back. This next example is how we apply the radar for the bases. Here we see this concentration of bases on King George Island, the Russian base, the Chileans have few bases, the military base and the scientific base, although one base has burnt down now. But when we were there, it was still up. Here's a high-resolution radar image. We've taken the example of the Russian base, the Chilean bases, and the Chinese base. We've processed the images. Here you have a magnification of these areas, and these are our classifications. We can determine the buildings and structures, the compacted surfaces, bare soil, sparse vegetation, water surfaces. And we can see the area which they occupy. And we can get a pretty good idea of how these bases are actually having an impact in these areas. So being able to monitor the activities is also important. And what's happening nowadays with a lot of the bases, they're increasing in size. So monitoring is very, very, very useful, and also for the conservation. King George is an exceptional, is exceptional because there's so much activity. It's a gateway to Antarctica through planes, through ships, etc. So it's an area which should be monitored, and also the conservation is important. And one of my last examples is using interferometry. Now, this is extremely interesting, especially when we're talking about ice-free areas where you have permafrost. Permafrost can have the effect that the active layer increases and subsides between the different seasons. And this can actually be detected with radar, a satellite. We've used simple examples and data which was available. We have to be careful here as well, because we're just at the beginning, and these are preliminary results, and it's complex to carry out interferometry. We have some experts in the team which are working with it, and what's important when we carry out this kind of processing is that we have enough data available. Here we're obtaining data every 12, 14 days, which is a big gap of data time-wise. What we would need is 6 to 7 days between images. We're obtaining this now through different sensors. Here we use Sentinel-1, which is available to everyone, but there are other sensors which we've got research projects with, and we're obtaining these data. So in the future, we hope to improve this data, because you will observe that the differences are minimal here between the colors. Actually, we're in such a small range that we're probably in an error range, because the Sentinel-1 data is with a pixel which is much too big for obtaining the sensitivity. That's why there's not that much difference between one area and the other. But once we get better resolution data over time, over space, then we should be able to obtain better results. Here we're also limited with the data we obtain, because we only obtain one polarization, which for radar is little. In other areas of the world, we have more polarizations, so we can obtain better results. And also, we just obtain data which is what they call in descending mode, when the satellite covers that area. In other areas of the world, you have descending and ascending mode, so you have many more images. So here we're a bit limited, but I think it's going to improve in the near future. Why? Because there are future missions coming along. This is a really exciting time for someone who's in remote sensing, because technology has improved. You have better sensors, better hyperspectral sensors in the optical region. You have better radar sensors. I've marked here in red the optical chime sensor, which will be in continuous. At the moment, it's just available as a experimental sensor. But these sensors will obtain data in continuous. It means that they'll be taking data of the whole surface of the Earth. And the same with the radar. The radar will be not a C-band, which we've always had, but an L-band, which will improve. With the bands, the longer the wavelength, actually you have the capacity of penetrating the soil, which is very interesting. Of course, the conditions of the soil, the drier, the better. But anyhow, we can penetrate the subsurface, and that's also very interesting. And then even more exciting is that it's not just ESA which is creating these future sensors, it's all the space agencies, NASA, the Japanese, the Canadians, etc. And nowadays, they've agreed, which is really helpful, to coordinate and collaborate. So one of their sensors obtains data, another sensor from another agency obtains data, and it's all available. And that's, of course, the best option one can think of. I started with remote sensing 30 years ago, and that was not available. You had to go and buy your Landsat images. Nowadays, it's available free. And these images will also be available for free. So it opens up a lot of possibilities. So just to come to a few conclusions, I won't go through them all, but it's very important that we characterize these ice-free areas. Field observations are absolutely necessary. Although we have satellite images, we have to calibrate, we have to validate our satellite data. We don't get around that. Site-specific information, like a spectral library, is key to all of this. If we don't have that, we don't really know what we're classifying. Using high spectral resolution optical satellite data, such as what we have available at the moment, EMMAP, we can actually get a quantitative data of soil properties if they are bare on the soil. With laboratory spectroscopy, we can predict soil properties of spectra, and we can create models so that we can measure easily more soil samples in a short time. It's obvious that the radar sensors have the advantage that they can always obtain data, but I think what we're aiming for is to combine the radar data with the optical data. Like this, we have the best of both worlds, and we can obtain more information. And the incorporation of future satellite sensors will, of course, accelerate all the information which we have. It'll probably be a problem of being able to process it all. But if we have systems already set, I think we can cope with it. We can obtain much more updated information nearly in real time. The problem is creating the processing chains and being able to interpret all the data. And like this, just acknowledgements that we've been able to carry out all this work with a number of projects we've had. Also, always the field work is supported by the different Antarctic programs. Doesn't matter if you come from Spain, from Chile, from Argentina, from wherever. You'll always get the support. That's the great thing of Antarctica. And also the remotely sensed data, which is provided by all the different space agencies. So thank you. And I would also just like to point out that of all the people involved in the ongoing project, we have a number of institutions which are involved, and they all do their part, not just in remote sensing, but also to be able to interpret what we're actually looking at in the field, the hydrology, the geology, the soil, etc. So thank you very much.
It's now time for questions from the public. Is there any question?
I can start. Thank you for the presentation. It has been very nice. For me, it's amazing all the things that you can get with the satellite image. So I would like to ask you, because when you analyze the soils and the biological covers, you say that you have the spectral signal of the lichens and the mosses, but have you also tried to differentiate lichen species or lichen communities? Is also possible?
Yes, of course. You can differentiate them. The spectral curve which you obtain will be different for one species to the other. Of course, you have to characterize very well the species you're looking at and in what conditions they are. It's not the same. Vegetation has a cycle, and the mosses and lichens also have a cycle. So you have to probably obtain spectra from different times. But there'll be certain characteristics along the spectra, absorption, points of absorption, which will be characteristic for one type of lichen or the other.
Yeah, for example, in this aspect, when you have the lichens, also can have different signal in their hydrated or dehydrated. Also, you analyze this?
Yes. You'll see the signal. If it's dry, then there will be certain parts of the spectra which will have an absorption feature. And if they're hydrated, your actual signal will go down because of the humidity, yes.
Okay, more questions?
Yeah, I would like to go one step forward, even not only distinguishing lichen species, but can you actually see microbial metabolic activity in soils compared to others? Because I'm thinking of these new defrosted areas will come in the next years. They will be colonized, and there will be new active areas or not. Can you identify metabolic activity in different areas, differentiate?
What we've done so far, we have people which are microbiologists, so they were interested in seeing what kind of microbes are in the soils. So we've been analyzing this, and we've been trying, that's why I had the example when you have a vegetation cover and what the sample underneath is like. And from there we can get a characteristic curve of that soil. However, if you're looking at microbial activity, it will depend on the organic matter, on the clay type, etc. There'll be a whole combination, because what the spectra sees is everything which you have in that soil. However, if you do an analysis which is directly with soil respiration or some kind of parameter which is of your interest, you can statistically look if there's a difference between what you have, if there's a high activity, microbiological activity, or if there's a low microbiological activity. And there you have to go through regression analysis or AI.
Thank you, Thomas. I really enjoyed your presentation. Probably you mentioned, but I didn't get it. Mm-hmm. Which is the resolution of these new generations of satellites?
Well, that's a very good question. These new satellites will have actually a same spatial resolution as the ones which exist, which are 30 by 30 meters. 30 by 30 meters.
How can you distinguish a lichen species in this?
Well,
With this resolution.
the thing is, you have techniques to what they call unmixing, and within your pixel, you can see an area which is dominant with one species compared to another, and you can work out percentages. That's not that much of a problem. The advantage of the new optical sensors will be that you have a higher spectral resolution, so you can see many more details, and you'll have time-wise, you'll have a repeated coverage. The only thing is Antarctica is limited because of the weather conditions. But if you're looking at 30 by 30 meter, as you said, then you have a coverage. Your lichens will have to be representative over a bigger area. They can't be small patches of 1 meter by 1 meter. For that kind of work, you would have to use drones. Actually, we've started using drones exactly for that. But the drones don't have the capacity of this spectral resolution which we would like. But there are techniques to be able to differentiate with the percentage. Of course, many times when I'm in the field, the soil is what interests me. But what is really important is the composition of your lichens and mosses and stuff. And that is what creates your soil processes, really. So the more variety you have, the better for the soil, really. So we have been able to detect differences between the vegetation if it's just pure lichens a typical usnea, or if it's a thick carpet of moss, or if there's a mixture. That we can differentiate well. Okay.
Okay, more questions?
Thanks, Thomas. Such a beautiful presentation and very pedagogical for the ones that we don't understand in deeply the sensors. And in that sense, I would like to ask now if we were working with one of the commercial satellites that it's SAR, and it has 0.5 meters resolution, and it can be triggered remotely and go to the desired place to take the image. Does it make sense to, for example, to get ready if you are in Antarctica, there is a beautiful day, and then you go out, you trigger your satellite, and you take the picture with nice resolution and nice field sampling? Does it make sense?
Yeah, if you can manage that, of course it makes sense. The best is if you can combine your field data with the actual image being acquired at the same time. That's the best result you can have. When I'm working here in Spain doing this, it's not that much of a problem in summer because we have good weather and we can do that. The only thing is the logistics behind it. If you're in Antarctica somewhere and you're expected to be in a place at a certain time, you'll be lucky to be there. If you're at a base, maybe it's more likely. But if you're going by ship from one place to the other, you're going to have problems. And that the weather is stable is not that you have 3 days of good weather. You'll probably have a window of a few hours and then it can change. So it's really, that's why the example which I gave was just fantastic. But it's very difficult to organize that.
So you don't think that the satellite can come to your place that fast? Because we were using it for flood inundation areas to estimate that with the SAR, and it was triggered with the rain. So it should be...
But it's SAR image, not optical.
It is SAR.
SAR. Then SAR, that's more likely, of course, yeah. That you can be at the same time. I understood you were with optical data, but if you're with a SAR image, then it's possible. The only thing is, again, with SAR, it sounds very good because it can be taken in all weather conditions, but it can be affected by the humidity, it can be affected by many conditions which will also have a different signal. So there again, if it's good conditions, better.
Thanks, Thomas.
Okay.
We have more questions from the public? No. I have just a curiosity.
Go ahead.
So maybe it's a simple question, but you were showing what is in the ice-free areas, but I was wondering what is below the ice now. So is it soil formed many years ago? Mostly rocks?
Well, under a glacier, it can be many things.
Many things, okay.
It can be even a lake which appears. The thing is, many times when the ice front recedes, then there's a lot of fluvial, what we call paraglacial conditions, and so a lot of sediment is being moved. And that, of course, can destroy if a soil was there at one time. To have an actual soil intact under a glacier, it's possible. I've seen it in the Alps. But it's normally in an area which was a kind of pond or something where it was conserved, the water disappeared and the soil stayed, and it's within a kind of, it's kind of protected. If it's just in a flat area or in a slope, then it can disappear.
Okay, so this is very heterogeneous and will depend on where are you in Antarctica?
Of course, yeah. I mean, what's good when we're looking for soils, we're looking for stable areas where there's no erosion, of course, where vegetation can colonize, where vegetation will stay, where soil processes can be active. We also have to think that during the short summer, temperatures don't rise much, but the biological, the chemical processes are just active for a very short time. So it takes a very long time to create a soil, really. Much more than here, of course.
Okay. Thank you very much. More questions? So we are done. We can continue talking with Thomas at the kiosco. We will be there for a while. And thank you very much for coming, and Thomas for the talk.
Thank you very much.